Good afternoon, everyone. Welcome to the live problem solving session for week 6 of traffic engineering course. I am Sedu Vinayagam, a PhD scholar in the civil engineering department at IIT Madras. Okay, so let's begin with an overview of what was taught in week 6 of the course. Okay, so till now we were looking at a level of service analysis, capacity analysis for different type of facilities, right? Like multi-lane highways, freeways, two-lane highways, urban streets, and so on. Right. So this particular week, so we were looking about intersection control, and critical aspects of how the intersection controls are operated. Okay. So this means that we are looking at urban intersections where there are conflicts. Okay. So in the first lecture, so we are looking at what is an intersection and what are conflict points. Okay. So what is an intersection? So intersection is nothing but when you have conflicting or opposing traffic movements meeting at a place, right? So if you have a movement that is east west bound, okay, like this, and that meets something like a north south movement, okay. So here you have north south movement, here you have east west movement. Okay, so these opposing traffic movements, so when they are meeting at a particular space, so there will be conflicts arising, right? So and this point is what we call as the intersection, right? So they are merging or diverging or crossing each other, right? Different movement of traffic. So conflict point is basically wherever these different traffic movements cross or touch each other, right? So how can this happen? So when you have eastbound movement like this, and there is a northbound movement, right? So this is a conflict point, right? So these two traffic movements are crossing each other. It's not just crossing; it could be diverging as well, right? So even from the same direction. So when there is one through movement and there is one right turning movement, these are happening. So this point where the traffic diverge from each other, so that can create a conflict point. Similarly, we could have a merging conflict. So when traffic from a through movement merges with a turning movement, so we can have conflicts there, right? So or we can have crossing, but from turning movements, two different turning movements from different approaches, so they can cross each other, and there also will get conflicts. Okay, so like this, so there can be a crossing, there can be a merging or diverging. So when these happens, we call those points as the conflict points. So at intersections, depending on how the traffic movement happens, so any of these kind of conflicts can occur. Okay, so that's why these conflict points are dangerous conditions, right? So they can lead to accidents. So that's why we need to control the movement of traffic at these intersections so that we increase the safety of the traffic. So next we looked at level of intersection control, right? So we can provide these intersection controls at various levels. So we have three different levels, right? So level 1, level 2, and level 3. So level 1 is called as passive control. So what happens here? So in passive control, you do not have anything like signals or signs or anything. So there is no physical equipment or device that actively tells the traffic you have to do this. A particular driver. So there is nothing that tells a driver what they have to do explicitly, right? So what happens? So then how is the accidents or conflicts avoided? So it is avoided through what we call as the basic rules of the road, right? So there are basic rules, right? So that define who has the right of way, right? Who can use the particular road at what time, right? So those are the basic rules of road. So that must be followed by different by the drivers who are passing through the intersection to avoid the conflicts. So we'll for this we'll have different guide signs, road markers. So these kinds of markings and signs are used to guide the drivers. So what are the different basic rules of the road? So with respect to right of way, if we see, so suppose we have intersection like this, right? So and the vehicle is approaching this intersection. Okay. So when the vehicle is approaching this intersection, let's call this vehicle A. Okay. And when it is approaching, if there is another vehicle which is already that has entered into the intersection, okay, or if there is a pedestrian, it could be a vehicle. So B could be a vehicle or a pedestrian. Okay, but B has already entered the intersection when A is approaching the intersection. So in this case, what does the basic rules of the road say? It says that A should yield. Okay, A should yield, which means that A should slow down, allow B to pass through, and then once a gap is available, right? So A can pass through. Okay, so which means that B has the right of way. One whoever has already entered the intersection has the right of way, so they must be allowed to pass through, and then whoever comes next, then depending on what the condition is, they have to make a call next. Okay, so that is one of the rules of the road. But if there could be another condition, right? So where two vehicles, okay, so A and B are approaching, right? No one has entered the intersection yet, but two vehicles are approaching nearly at the same time. So in this case, who should enter the intersection first? So the rule says that the vehicle that is on the left, right? So in this case, it is vehicle A is on the left, vehicle B is on the right, right? So the vehicle on the right will get the right of way. Okay, so vehicle on the left should yield. Okay, so A again should yield to B. Okay, because B is on the right, right? So this applies for any pair of approaches. Okay, so whichever approach is on the left, so they have to yield for the movement happening on the right. Okay, so this is the basic rules that must be followed. If there is no other explicit control that is applied. Okay, so this is the passive control, right? This must be followed. So this you can do when the amount of or the volume of traffic is low. Okay, but when you have slightly higher level of traffic, so this cannot work effectively. So in that case, or if more accidents are happening just by following the basic rules of the road, so you go for a higher level, that is level 2, which is called as semi control. Okay, so what do we have in semi control is basically we'll have channelization, so which means so we'll have roundabouts or channelizing islands. or we can have signs like yield sign and stop sign. So these things come under semi control, right? So where so in channelization, so we have a physical feature which separates the different movements of traffic, right? So for example, when you have a channelizing island, something like this on an approach, so where there can be a left turning movement and there can be a through movement, right? So in this case, what we are doing, so we are physically separating the through movement from the left turning movement. So the diverging conflict is avoided in this case, right? So that's how the channelizing islands can help. Or if we have a roundabout, right? So if we have a rotary or a roundabout, so what happens in this case? So people will enter and then they will move in the clockwise direction, okay, and then they can leave. So here the rule is the right of way lies with the vehicles that are in circulation, right? So a vehicle has come in and they are moving through, and the vehicle then that is trying to enter, they have to yield to the vehicle that is already um, within the roundabout, okay. So this vehicle in circulation has the right of way. Or if we can have yield signs and stop signs, okay. So what is the difference? So how does the yield sign look like? So the yield sign will be a triangular sign which is pointing downwards, right? So we'll have give way, return in the middle, and the stop sign is the most familiar one, so it will be the red octagon, okay, with stop return in the middle, okay. So what is the difference between the yield sign and the stop sign? So yield sign means the vehicles that are coming towards the intersection, so they will have to slow down, right? And if the condition is not safe, they have to come to a complete stop, and then when they have a safe gap available, cross through, okay. But if once they slow down, if they have enough gap available, they can pass through without stopping as well, right? So stopping is not necessary in the case of yield, okay. Only if it is required, the vehicles have to come to a complete stop. But if there is a stop sign, it means that whether or not there is a safe gap available, the vehicles must come to a complete stop and then look at the conditions, then proceed. Okay, so whether depending whether or not the gap is there, the vehicles must come to a complete stop in the case of a stop sign. Okay, so these two also can be used for semi control. So, but if there is even higher level of volume or more conflicts, right? So in that case, we can go for the level 3. So in level 3, we can have signalized intersections, right? So in signalized intersection, we provide traffic signals, okay? So where we change the right of way by using the traffic signal, right? So instead of the basic rules of the road, so where we said left has always must always yield to the right. So we are trying to change that explicitly using these control devices. So how are we doing it? So we are separating the traffic in a temporal way, which means that during the cycle where in a cycle, so when one approach gets green, okay, so movement will happen here, and the movement in the other approaches will be stopped, okay. And then after some time, when green is coming here, so the movement will happen here, and the movement will be stopped in all the other approaches, right? So we are providing the right of way to the different traffic movements in by separating them in a temporal manner, right? So at different times, different approaches get the right of way. So that is explicitly altered by using the these traffic control devices. Right, those are the different levels of intersection control, and then we looked into the passive control in detail. So where we discussed these right of way rules and everything. So in the second lecture, we are looking into semi control and active control. Okay, so as again we discussed that in detail. So in active control, we can have different types of signals. So we have basically two major types. One is the pre-time signal, another one is actuated. So pre-time signal means so the signal sequence, right, and also the cycle length, the green time, red time, everything will be fixed. Okay, so they keep repeating cycle after cycle, right, without any change, right? So there won't be any variation in the cycle length or the phase sequence or the interval length. Okay, so that is called the pre-time signal setting. Another is the actuated. So actuated means so depending on the type of traffic that is coming in, right? like whether only through movements are coming or some turning movements are coming, and the volume of these traffic movements. So that determines the phase sequence as well as the interval lengths. Okay, so which means like if there are no traffic movements coming, no turning movements are coming, say during 115-minute period. So in that case, there is no need for a phase that gives the signal for left turn or right turn, right? Only through movements can be allowed. So those kinds of changes are possible in the actuated signals, which means that so from cycle to cycle there can be variations in the phase sequence and also the cycle lengths. So that is the actuated signal. And then we looked at data requirements for justifying traffic control signals. So how do we, so we will not put traffic signals at every intersection, right? So how do we know where we have to put the traffic signal? So we need to justify that. So for that, we will be collecting data. So what kind of data? It's like the data related to the traffic volume, right? Then we have pedestrian volume, like the type of accidents, and the number of accidents that are occurring. So these kinds of data are collected in order to study whether or not a signalized intersection is required. Okay. Then in the third lecture, so we were looking at two different code books, okay, which talks about whether traffic signals are should be provided or not, right? So the first one is the MUTCD, which is the manual for uniform traffic control devices. So this is from the US. So it talks about signals and also other traffic control devices, right? So we have signs, markers, right? So it talks about all of this. In that, there is a section for the warrants for traffic signal control. So what does this mean? So it lists actually 9 different warrants. So warrant is nothing but a particular condition. Okay, so depending on so again we have 9 warrants, means 9 different conditions. So like 8-hour traffic volume, 4-hour traffic volume, pedestrian volume, and so on, right? So there are 9 different conditions. So if on any of these conditions are satisfied, okay, so then it means that the signal, the intersection might benefit from having a traffic signal. Okay, it does not enforce this like a rule, but it suggests that suggests us to look into that particular intersection whether it is suitable or not for a traffic signal. Okay, so if any condition is satisfied, we have to go for an engineering study, so where we will be collecting all this different data and then look whether we can reduce the accidents or the delays by having the by installing the traffic signal there, right? So that those are the warrants. So this MUTCD gives 9 different warrants, and for Indian conditions, so we have the IRC 93, okay, which gives traffic warrants for the Indian scenario. Okay, so here we have 5 different warrants. Okay, again talks about the traffic volumes, accidents, pedestrian volumes, and so on. So depending on this, when one warrant is satisfied or a combination of different warrants are also satisfied, so we should go for a engineering study to determine whether that intersection will benefit from a traffic signal or not, right? And then we have to decide whether we will give it or not. Okay, in the fourth lecture, so we moved into looking at closely at the signal controls. Okay, so we're looking at signal controllers and different operational characteristics. So here only we were looking at this pre-timed and actuated signals. So when we talk about signal, so some basic terminologies we should be familiar with. So first is cycle. So cycle is nothing but a sequence of phases. Okay, so what is a phase? A phase means a particular type of traffic movement is allowed in a particular phase. Okay, so for example, so when we have a through movement from one direction or a through movement and the right turning movement happening. Okay, so this is called a particular phase, right? And then once this finishes, we may allow the north through movement or north through movement along with maybe left turning or just turning movements alone. Okay, so which means one particular set of movements, so which happens separately. Okay, so that is called as a phase. So what we call as a cycle is basically a sequence of different phases, and when we come back, so this phases will come back to the starting position, right, and repeat. So when it comes back to the same position, so we call that as one cycle, right? And then we have interval. So interval is basically how long a particular signal indication lasts. How long an indication lasts. Right, so we have the red signal, green signal, and amber, right? So when it is green for one phase, right, so it will be red for the other phases, right? So and this other approaches, and this will be there for some time, and then after that time elapsed, the signal indication will change for the approaches, right? So this how long it lasts for is called as an interval. Okay, and then we have cycle length. So what is cycle length? Cycle length is basically how long one cycle lasts, right? So if starting with say green for a particular approach, right, how long it takes to get the next green, right? So that is the cycle length. Okay, time taken to get the same indication again. Okay, so these are the different terminologies that we should be familiar with. And then we looked at different ways of grouping the traffic movements. One is movement group, another is lane group. Okay, so what happens in movement group? Okay, so movement group is basically so exclusive turning movements. Exclusive turning movements will be forming their own movement group. Exclusive turning movements have separate movement group, right? So rest of the movements will be forming one movement group. So what does this mean? So suppose we have in an intersection, so we have one, let us say, left turning movement, and there are two lanes where right turning through movement is there, and then let us say there is a through movement shared with a right turning movement. Okay, so in this case, how many movement groups are there? So there are two movement groups here. Okay. So here we have an exclusive left turn. What do we mean by exclusive left turn? Which means that in this particular lane, okay, in the extreme left, so we have only left turning movements that are happening from that lane. Okay. So there is no other movement that happens from that lane. So which means this is an exclusive left turning lane. So according to the movement group rule, so this should be movement group 1. Okay. It is a separate movement group. So and then looking at the rest of them. So here these two are through movement. Here what is happening? There is a through movement shared with a right turning movement. Okay, but the movement group is one for the turning movements if it is from an exclusive lane. But here the right turning movement is not happening on an exclusive lane. It is shared with the through movement, right? So therefore this is a shared turning movement. So it will not get a separate movement group. So which means this through and the through plus right turning will form another movement group. Okay, therefore there are only two movement groups in this. Okay, so whereas if you look at the lane groups, so that is different. So lane groups, how does it change? So here, so if you look at lane groups, there will be three lane groups here. So the exclusive left turn will get its own lane group. So this will be lane group 1. The two through movements, they will form a lane group 2. And then this through plus right turning movements, so this will form a separate lane group. Okay, so here we will have three lane groups but only two movement groups. Okay, so in analysis we'll go with either movement group or lane group, right? So movement groups will make the analysis little simpler, but when we are designing signals we'll go with the lane groups actually. Okay, next in the fifth lecture, so we were looking at some some more concepts related to signals and their working. So one is the saturation flow. So what is saturation flow? So before saturation flow, we should look at how the headway varies when a signal turns green. Okay, so if you look at this, if you plot the headway as a function of the vehicle that are crossing, so this is headway and this is vehicle number. Okay, so how do we calculate this headway? So we have at the intersection, so we will be having the stop line here. Okay, so when the signal turns green, so the first vehicle, the time taken by the first vehicle's front wheel to cross the stop line, from the time of the signal turning green, so that is the headway for first vehicle. Okay, time of green to crossing the stop line. So, and then headway for the second vehicle is the time to cross the stop line by the first vehicle to crossing the stop line by the second vehicle. Right, so by number 1, this is by number 2, and then so on. Right, so this is how we calculate the headway for the different vehicles. Okay, and then if we plot those, we'll get a plot like this. So initially we'll see that the headways are higher, right? So maybe after 3 or 4 vehicles, what we will see is the headway reaches a constant value. Okay, and this constant value is what we call as the saturation headway. Okay, that is our saturation headway. So what does this mean? So the saturation headway is basically the average headway that we can expect. So which means that if the signal was not there, okay, or if the signal remains green all the time, right? So this is the so the vehicles can move at this saturation headway, right? And the corresponding capacity, right, or the flow that takes place at the saturation headway is called as the saturation flow, right? So which means that the saturation flow is nothing but 3600 by the saturation headway. Okay, so this h is nothing but this constant value. Okay, so if the signal remains green always, so vehicles can go through without any delay. Okay, and this is the maximum flow that we can see, right? So equal to the saturation flow. And then we have loss times and intervals. Okay, so loss time is basically, so as we looked at, so the initial 3 to 4 vehicles, so they will have a higher headway than the saturation headway, right? So which means, why is that happening? Because the drivers at the front, so they, once the signal turns green, they will take some time to react to that change, right? And then they have to accelerate, right? So that requires some time, right? So that time, so if we add up all those times for the first 3 4 drivers where it is higher, so we get the startup loss time, right? So this is called as startup loss time. Similarly, there is another loss time called as the clearance loss time, which happens at the end of the cycle, right? So what happens at the end of the cycle? So so the signal will be green. So before it turns red, it won't immediately turn red, right? It will turn into amber, and then it will turn into red. Okay, so why is this amber there? So this amber is there to warn the drivers that there is going to be a change in the signal phase, right? So green is going to end and red is going to start. So amber warns the drivers of this change that is going to happen. So what happens? So when drivers look at the amber, so they will slow down their vehicle, right? They will slow down the vehicle, and if they are not able to cross the intersection, right? So they will enter the intersection. If they have entered the intersection, they will cross. But if they are not able to cross, they will stop their vehicles. Okay. So because the vehicles slow down, right? So there will be some, the flow will be lesser than the saturation flow rate, in that amber period. Okay. So that also leads to some time that is lost. So that is the clearance loss time, and the sum of these two, startup and the clearance loss time, is called as the total loss time, right? And then we looked at the different intervals, right? So we have the green, yellow, and then we have all red interval. Okay, so what is all red? All red is basically, so when the amber signal is there and somebody has entered the signal, entered the intersection, right? So but the signal has turned red, right? So in that case, they have to leave the intersection, right? So no other traffic should enter at that point, right? So for safety, so there will be a period where all the 4 sides, right, so they will be experiencing a red signal. So this is called the all red period. So this is there because to clear the vehicles that have that are within the intersection. Okay, so that have entered legally during the amber phase, but they need some more time to leave the intersection, right? So that's where the all red period comes. And then we looked at capacity of lane groups, arrival times, and Platon ratio. So what is the capacity of a lane group? So we looked at the different lane groups, right? So how we will classify the lane groups. The capacity of a lane group is nothing but the maximum of the different lane group volumes, right? So here in this case, so lg1 will have one volume, let us say v1. lg2 will have v2, and lg3 will have v3. So the maximum of this v1, v2, v3 is called as the critical volume, or the critical that is the critical lane group. And then we looked at arrival type. So arrival type is basically we are looking at how many vehicles are coming in in a particular cycle, right? And then characterizing that particular uh, type of arrival. So what do we do here? So the arrival type is based on value called as the Platon ratio. Okay, how do we calculate this? It is equal to P by G by C, GI by C. Okay, for a particular phase or particular approach. Okay, for approach I, it is P by PI by GI by C. Okay, so what is PI here? So PI is nothing but the proportion of vehicles arriving in green time, right? So vehicles will be arriving at all the time, right, in the signal, right? So some will be arriving during the signal is green, and some vehicle will arrive when the signal is red. So we take the total number of vehicles that are arriving in a cycle, and then look at what percentage of the total came in the green time, right? So that is PI. And then this GI by C is called as the green ratio, the effective green ratio. So what is this? This GI is nothing but is called the effective green period, effective green, and C is your cycle length. Okay, so what is effective green? So effective green is different from the green interval, right? So green interval is for how long the signal remains green. Effective green is for how long the vehicles can actually move, right? So why are these two different? So because I said right, the vehicles can move during the amber and the red period also, right? So the not in the red phase, during the all red period, right? So that is not equal to the green time, right? So the effective green, which is represented by small g, is the green time plus the yellow interval, right? So vehicles can move through the yellow interval as well, plus the all red interval. Okay, so this is the extra time that the vehicles get, but all of this extra time is not utilized, right? So we looked at two lost times, the clearance and the startup lost time. So those two lost times should be removed. Okay, so if we do that, what we get is the effective green time. Okay, so this is the total period in which vehicle movement happens in a particular cycle. So this effective green divided by the cycle length, this is called as the effective green ratio, right? So this proportion of vehicles divided by this green ratio gives us what is called as the Platon ratio. And depending on the Platon ratio, we have 6 different traffic arrival types. Okay, so we have 6 different arrival types. Okay, 1 to 6. So 1 is very poor, and 6 is the best one. Okay, so so you can have like it will vary from starting from 0 to up to 2. So 0 to 0.333, right? So one third, right? So one third of the vehicles are arriving during the green effective green time. Okay, so this is a this is called as poor progression. Okay, so why? Because see, most of the vehicles, so if the vehicle is arriving during the green period, so which means that they are going to, if most of the vehicles are going to arrive through the green period, so the total delay that the vehicles are going to experience is low, right? So if they are arriving through at the red time, so they have to they will form the queue, and then they will be delayed more, right? So here type 1 means, so more vehicles are experiencing delays, right? So which means more vehicles are coming during the red period, right? That's what the lower value of this Platon ratio means, right? So Platon ratio, as we saw, it is PR by GA by C, right? So when will this happen? This happens when PA is small or GA by C is large, right? But this GA by C will be a fixed value. Okay, for a given signal setting, this GA by C will not change. Only PA will be dependent on the demand, right? So if PI is small, so which means that more vehicles are arriving during the red time instead of the green time, right? So that means the progression is poor. Vehicles have to stop for a long time. So the other extreme is 6. So 6 means that most of the vehicles are coming during the green time, which means that they are not experiencing any delay, right? So that's how we are classifying this arrival type that is happening at the intersection. So that's where the arrival type and the platoon ratios are used. And then finally, we were looking at a performance measure for signalized intersection, which is delay. Okay. So far, so when we are looking at or quantifying the LOS for highways, so we were using different performance measures, right? So like density for freeways, freeways and multi-lane highways, and then we had the average travel speed, percentage time spent following, and the percentage of the free flow speed. So these were used for two-lane highways, right? So and then the speed was used for urban segments, right? So that like that, depending on the facility, we had different measures of the level of service, right? So for signalized intersection, we have delay as a performance measure, right? So here there are different types of delay as well. So we have stopped delay. So stopped delay means it is the time the vehicles are in a complete stop, right? So how for how long the vehicles are in total stop movement. And then we have approach delay. So approach delay is, so before the vehicle comes to a stop, so they have to decelerate, right? So when they are approaching the intersection, so they'll be coming at some speed. Then they look at the signal, they look at the queue, and then they decelerate and then come and then join the queue, right? So the some time is spent, some time is lost because of this deceleration moment, right? So that deceleration delay plus the stopping delay is together called as this approach delay. And then we have the travel time delay. So the travel time delay is basically, so when you didn't have the intersection, how long it would have taken to cross that particular point versus how long is spent to cross this point because of the signal, right? So the difference between those two times is called as the travel time delay. Basically the difference between uh, you know with the time taken with the signal and without the signal. And then we have, yeah. Sorry for that interruption. So we are looking at these different types of delay and then different delay scenarios. So and then there are different theoretical models that look at quantifying the delays. Okay. So we have three different delays. One is the uniform delay, right? And then we have random delay, and then we have overflow delay. Okay. So what happens? So whenever we are looking at this delay analysis, so we'll use the cumulative count curves, right? So in one of the earlier problems, in the previous week, so we have used this. So where the y-axis will tell you the cumulative number of vehicle, arrivals and departures, cumulative arrivals or departures, and the x-axis will tell you the time. Okay, so you have an arrival curve. Okay, if we assume a constant rate of arrival, so we'll have a linear curve like this, and then departure curve. So how will they be? So initially So it varies, right? So the rate of departure will depend on the signal now, right? So because vehicles cannot pass through this intersection all the time, so during the green phase only they can pass through, and during the red phase they have to be stopped. Okay. So during the green phase, so assume that it starts at green. So first, all the vehicles that are coming in will go out, and then once the signal turns red, the vehicles must stop. Therefore, the departures will not change, right? So it will be a horizontal line. And again, when the signal turns green, so the vehicles will go through, and they can catch up with the arrival curve, and then they will again go through with the arrival grid. And for the next cycle, again, this red phase, the vehicles will stop, and this will keep on going. So this happens in undersaturated condition, right? So when the demand is lesser than the capacity, so depending on the saturation flow rate, the capacity will be different. So if your demand is low, so then you will have this condition where the vehicles that that are stopped or in the queue, so they can be cleared in the same cycle. Okay, so they won't go into the next cycle. So all the vehicles that are queued up will be cleared in the same cycle. So in this case, so you'll have what we call as the uniform delay, because this this triangular area, so this will be repeating in every cycle. Okay, so and also this area of this triangle is nothing but the delay. Okay, so as we saw, this horizontal distance is nothing but the delay for a particular vehicle, and the vertical distance is the queue length at a particular point in time. Okay, so vertical distance is queue length, horizontal distance is delay, right? And the area of a triangle will give you the total delay. Okay, for all the vehicles. So in each cycle, the total delay will be the same. That's why we are calling it as the uniform delay. Okay, right? So this happens when the demand is low, at low demand conditions. So then we have the random delay is sometimes in some random cycles we'll have higher demand, right? So mostly it will be uniform, but in some random cycles, so delay will be higher. So it can so it may not always catch up with the arrival curve, right? So there may be some spill back into the following cycle, right? So that happens at randomly at different cycles. So that is the random delay. Finally, we have the overflow delay. So in overflow delay, what happens? So the capacity is not enough. Okay. So when we have overflow delay, so signal stops. But once the signal turns green, the departure curve does not catch up with the arrival curve, right? So before the vehicle, the queue gets cleared, so again a red signal happens, right? So because of lower capacity, and then the queue keeps growing, and then again there will be clearance, and then it keeps growing, and like this. So in this case, what happens? The departure curve is not catching up with the arrival curve, so this area is going to keep on growing, right? So there will be a divergence between the arrival and the departure curve. So in this case, if you look at it, we can look at it into two different parts. So we can have a uniform delay part, right? So the area of the triangle in the shaded portion, this colored portion, so this will be your uniform delay part. In addition to that, you will have this overflow delay, right? So this excess delay, and that will keep growing if you have oversaturated condition, right? So until the demand comes down, this this overflow delay will keep growing. Okay, so we have different models for each of these different conditions. Okay, so those were looked at in the theoretical modeling part. And then we have looked at some inconsistencies in the random and the overflow delay model. So what is this inconsistency? So if you look at the delay values, as a function of V by C ratio. Okay, so delay as a function of the V by C ratio. So what happens is this vertical line, so this is equal to V by C ratio of 1. Okay, so this means at capacity condition. So what happens? A random delay model tells that when the V by C is 1, the delay goes towards infinity, right? So it is so large, right? But that is not true, right? So it cannot be infinitely large, right? So it has to be at a finite value. So that's where this random delay model fails around the V by C 1. So, and if you look at the right side, this is from the overflow delay model. So that says at V by C equal to 1, the overflow delay is 0, right? So though the V by C is not, V by C ratio equal to 1 is not oversaturated condition, it does not mean the overflow delay is always 0, right? Because of the random failures of the cycles, in some cases we will have some excess delays than the uniform delay, right? So saying that the overflow delay will always be 0, so that is also not realistic. So around this V by C ratio of 1, both this random delay model and the overflow delay model, so they are not, they won't give the realistic value, right? So that is what we call as this inconsistency in the random and the uniform delay model. So this is overcome by other type of models like the axiatic model. Okay, so these are the different things that we looked at, with respect to the intersection control and operations. Okay, now let's move on to some questions related to these. Okay, so the first question for this week is, which of the following statements is correct with respect to level 1 control at an intersection? Okay, the first is sufficient side distance is not essential for safe operation. Traffic signal is an example of level 1 control. The driver is expected to obey the basic rules of the road, such as right of way rule. And D is all of these. Okay, so you can put your answer in the chat. So you can take a moment to think about it and then use the chat to answer. Okay, option C. Any other answer? Okay, two answers for option C. All right. The right answer is option C. The driver is expected to obey the basic rules of the road, such as the right of way. Okay. So here we are talking about level 1 control. So as we saw, level 1 is nothing but the semi control. It's where we have yield sign or stop sign, or we have channelization, right? Like roundabouts, okay, or channelizing icons. So in this case, so we are looking at which statement is correct. So we'll cross out whichever is not applicable. So we know traffic signal is not level 1, right? So traffic signal comes under level 3. So B is obviously not right. So if B is not right, D cannot be right, right? All of these cannot be right. So A is sufficient side distance is not essential for safe operation. So this is obviously incorrect. So there must be sufficient side distance. Why? Because say we have a yield sign, okay? So what do the vehicles have to do? So say there is an yield sign here, which means that the vehicle that is coming from the going towards east direction, so the vehicle will have to stop, slow down, and then if it is safe when there is a vehicle that is not coming, or is it far away, so in that case they can pass through. So to make the decision, this driver must be able to see what is happening on the other approach, right? So which means this side distance must be available, right? So this is what we call as the side triangle. Okay, so the vehicle, if it is not safe, they must be able to come to a stop, right? So that stopping distance should be available for them by looking at the other when they are able to look at the other approach. Okay, so that is required for the safe operation. So A is also not right, so which means that C is the right option. Okay, C again, even though we provide this semi control, still the driver must obey the basic rules of the road, right? So as we saw in the roundabout example, so the vehicles that have already entered the intersection, right, so which are in the circulation movement, so they have the right of way. So the vehicles that are coming in, they must yield to the vehicles that are already in there, right? So such rules should be obeyed by the drivers. Therefore, C is the right answer. Okay, question number 2 is with respect to the MUTCD warrants, match the warrants given in column X with its corresponding principal reason given in column Y. So we have 4 warrants, warrant number 7, 2, 3 and 6, and column Y we have the conditions based on which the warrants are dependent on. So condition A is volume of intersecting traffic, proper platooning of vehicles, undue delay on minor street traffic, and severity and the frequency of crashes. Okay, we have some predefined matches given. Okay, you have to just pick one of the matches given here. Okay, option B. Any other answer? Okay. So the right answer is option A. Okay, so where 1 is matched with the 2A, 3C, and 4B. Okay. So according to MUTCD, as we saw, so there are 9 different warrants, right? So warrants, there are 9 different ones. So 1 and 2 are based on the volume of traffic. Okay, so 1 is an 8-hour volume, 2 talks about 4-hour traffic volume. Okay, so 1 and 2 are based on traffic volume. So 2 is based on delays during the peak hours. Okay, and 4 is for pedestrian volume, and 5 is for school crossings. Okay, 6 is the platoon progressions. So we looked at the progression ratio, right? So it is related to that platoon progression. Or this is also regarding the coordinated signal, right? So when coordinated signal is when one from one intersection, when you go to the other intersection, you basically, if you are able to cross through without stopping, so you will have a coordinated system. So that will give you a coordinated signal, will give a better platoon progression, right? So that is related to warrant 6. And warrant 7 is about accidents, crash experience. So warrant 8 is depending on the road network. And the final warrant is for intersections that are near a grade crossing. Intersections near grade crossings. At grade crossings, okay, which means at the same level there is a crossing happening and near that there is another intersection. So that is warrant 9. Okay, so therefore warrant 7, right? So warrant 7 is about the crash experience. So therefore it is it is matched with the severity and the frequency of the crashes. Okay, warrant 2, so it is related to the traffic volume, right? So 4-hour traffic volume. So it is the volume of the intersecting traffic. So warrant 3 It's about the delays during the peak hour, right? So it is undue delay on minor street traffic. And 6 is plateau progression. So therefore 6 is matched with here, and that is given in option A, right? So therefore option A is the right one. Okay. Okay, assignment 6, I think it is still open, right? So the due date is not over. So we cannot discuss before the due date. Okay. So if you have any particular concepts that you have doubts on, we can discuss that, but the exact assignment questions we can discuss only after the due date. Okay. So before that, we can. If you have any particular doubt, you can ask. The question number 3 is, which of the following statements is incorrect with respect to yield signs? Option A is full stop is always required to the approaches with yield signs. Option B is provided along a minor street approach entering a designated through highway. Option C, it can be provided for unsignalized intersection within a signalized area. And D is, it is used at intersections with a minor road and a major road where application of the right of way rule would not suffice. So we have to select that statement which is incorrect. Okay, option D. Any other answer? Okay, so let's look at the answer. The right answer is option A, that full stop is always required to the approaches with yield signs. Okay, so here we are talking about the yield signs, right? So as we saw earlier, so yield signs do not need, full stop always, right? So it's not mandatory for the vehicles to come to a complete stop if there is a yield sign. So the vehicles must slow down, right? So yield means, so must slow down. Okay, so this is required. So you must slow down, and if safe, so you slow down and then you assess, right? So whether it is safe to cross or not. So if safe, can directly cross without coming to a stop. If not safe, then you have to stop and then wait for a safe gap to cross. Okay, so that this means that it's not always that you are going to stop, right? Only in case it is not safe, you will be coming to a stop, and if it is safe, you will directly cross, right? So but you will always slow down. So option A says full stop is always required, so this is not correct. So this is the case for a stop sign. So if stop sign is there, then you must always stop regardless of whether it is safe or not safe to cross. You must always come to a full stop and then see, and if it is safe, then you have to cross, right? So this is not the case with the yield sign. So therefore A is the incorrect answer. So B, C and D, so these are the different conditions, right? So if any of these conditions are applicable, so in that case you will provide a yield sign, right? So B, C, D are correct options. Okay, so these are the conditions that require a yield sign to be placed. Okay, question number 4. Which of the following are characteristics of a pre-timed signal controller? Option A is variable green times. Option B, fixed cycle length. Option C, a fixed sequence of phases. And option D is used at isolated intersections. So this is a multiple select question. So one or more than one option can be correct. Okay, B, C, D. Any other answer? Okay. So the right answer is options B, C, and D. Okay. So as I said, there are like two types of signal controls, right? So one is pre-timed, the other one is actuated. So pre-time means it has a fixed cycle length, right? So everything is constant, right? So it keeps repeating after itself without any change depending on the traffic conditions, right? So the cycle length is fixed and everything within the cycle length is also fixed. So what do we have within the cycle length? So we have the different phases, right? And each phase has a particular interval duration, right? So the interval duration, that the sequence in which the phases occur, and also the total cycle length, everything is fixed, it will be the same and that keeps on repeating itself. And it doesn't vary depending on how much the traffic volume changes, or the traffic movements proportion is changing. So everything will be the same. So green times is also a particular interval, right? So green time is also fixed, it's not variable, right? So therefore A is not correct. And D, it is generally applicable for isolated intersections, right? So where there is no another signalized intersection at upstream or downstream nearby location, right? So if there is an upstream or downstream intersection, so in that case we try to go for a coordinated signal to have a better platoon progression, right? In that case we should have a variable or an actuated signal. So here it is not needed when you have an isolated intersection. So there we can have pre-timed controller. So therefore the right options are B, C, and D. Okay, question 5 is, with respect to the given lane configuration of a 4-lane road, which of the following statement is true? So option A is the total number of lane groups is 4. Option B, total number of lane groups is 3. C, total number of exclusive lane groups is 2. And D is the total number of shared lane groups is 2. Okay, so we have A and B as two answers. Right answer is option B. The total number of lane groups is 3. Okay, so why? Because exclusive turning movements will be considered as a separate lane group, right? So when we are looking at lane groups, so here we have an exclusive left, right? So which means this will be a separate lane group, and then we have two lanes for through movement. Okay, this is not shared with any turning movement. Okay, so these two will together form a lane group, which is lane group 2, and then we have an exclusive right turning movement, right? So because this is an exclusive turning movement, this will form its own lane group. So this is the third lane group, right? So therefore we have three separate lane groups. Therefore the total number of lane groups is 3. Okay, it's not 4. Okay, question number 6, accept or reject. Critical lane group represents that lane group in a phase which has the lowest flow rate. Okay, option B. Any other answer? Okay, option A. The right answer is B, that we reject the statement because it is incorrect. So why is it incorrect? Because the definition, by definition, the critical lane group is the one that has the highest flow rate, right? So it's not lowest; it should have the highest flow rate. Okay. So basically, when you have a signal phases, right? So when you have a through movement on the towards the east, two movements maybe uh, so here through and the right turning movements. Here this is forming one phase, let us say. Right? Let us say this is phase A, maybe phase B we have two movements. Okay, so in this case there will be some volume, right? So let us say this is VA1 and these two together are forming VA2 and this is VB1, VB2. Right, so we have some configuration like this. So for each phase we'll have a critical lane group. Okay, separate for each phase we have to analyze separately. So in this case, so we have VA1 and VA2. So the maximum of these two, let us say it is VA2. So that will so this particular lane group will be the critical one out of all the different lane groups in that particular phase. Again here, if VB2 is greater than VB1, so this will be the critical one, right? So that is how the critical lane group is defined. Okay, so in each phase, whichever lane group has the highest flow rate, that will be designated as the critical lane one. Therefore, we reject the given statement. Question 7 is, which of the following statements are incorrect with respect to the loss time at a signalized intersection? Option A is clearance loss time includes a component of only the yellow interval. Option B is startup loss time is associated with the first 3 or 4 headways as drivers react to the green signal. Option C, total loss time is the difference between the startup loss time and clearance loss time. And D is end gain is the sum of the yellow change interval and the red clearance interval. Okay, so we can have multiple options here, right? So multiple select question. So if you think there is only one right answer, it's fine, but there can be multiple options. You want to change your answers if there are multiple. So you got D and C. Okay, so the right answer is options A, C, and D. Okay, all the three statements A, C, and D are incorrect. Okay, so what are we looking at? So we are talking about loss times. Okay, so option A says clearance loss time includes a component of only yellow interval. Right, so that is incorrect. Why? Because so what happens? So you have the green interval. Okay, so then you have the yellow or the change interval, and then you have the all red interval. Okay, so where does this clearance loss time occur? It happens at the end of your green phase, right? So in this portion, so this portion is available for the vehicle movement, right? So vehicle can still move through the intersection during the yellow period and the all red period, but not all of this, yellow plus all red period is utilized. Okay, initially some portion of it will be utilized, but the vehicles will start slowing down. Okay, so this portion where the vehicles will actually use it, so that is the portion we call as the end gain, and they will lose some of this remaining portion, right? So that remaining portion that is lost is what we call as the clearance loss time, right? So represented by L2. Okay, so which means that L2 is not only having the yellow change interval, but it also has some component from the all red interval as well. Okay, so therefore saying only yellow interval is present or part of the yellow interval is only present is wrong, right? So it has yellow interval and also all red interval. So therefore A is incorrect. So B says startup loss time is associated with the first 3 or 4 headways as the drivers react to the green signal. So this is correct. So as we saw how the the distribution of the headways look like. So this higher headways are associated with the first 3 to 4 drivers, after which it becomes constant. Okay. So this time is lost because this extra time over and above the saturation headway, so that adds up to the startup loss time. So that is correct. And C, the total loss time is the difference between startup loss time and clearance loss time. This is incorrect because total loss time is nothing but the sum of the startup loss time and the clearance loss time. Okay, so it's not the difference but the sum. Okay, so that's why it is the total. And D is end gain is the sum of the yellow change interval and the red clearance interval. So this is also incorrect. Why? Because so the clearance loss time is nothing but the yellow change interval plus the all red interval minus the end gain, right? So because this end gain is the portion which is used for crossing the the intersection, right? So which means that it is not a part of your loss time, right? So that part is utilized. Therefore, that has to be removed from your yellow and the all red duration, right? So whatever portion of the yellow and all red that is not utilized, that goes to your clearance loss time, right? So that means the sum of that minus the end gain. So which means that end gain is y plus AR minus L2, right? So it is not just the sum of these two, but sum of those two minus L2, right? So that's why D is also incorrect. The question 8 is match the arrival type of vehicles at the intersection given in column X with its corresponding description in column Y. So we have 4 types: type 3, type 1, type 4, and type 6. And column Y says exceptional progression quality, moderately dense or dispersed platoon. C is poor progression quality, and D is random arrivals. Okay, so these are the matchings given. So you have to match the type with its description. Okay, option B. Okay, so the right answer is option B. Okay, so 1 is matched with D, okay, 2 with C, 3 with B, and 4 with A, right? So as I said, we have 6 different arrival types, right? So this is based on the platoon ratio, okay, platonic ratio. So and the scale is, so 1 is the poor one and 6 is the exceptionally better platoon progression. Okay, so basically it goes from poor to good. Okay, so that is the scale. So which means that you have to look at the order here. So type 1, so which among the different progression qualities, so C is the poorest of them all, which is poor progression quality, which means this must be type 1. Okay, so the next best one is should go for type 3. So so which is random arrivals. So type 4 is better than random arrivals, is moderately dense or dispersed platoon, right? So which means groups of vehicles are able to go through quickly. And finally, we have type 6, which is the best of the lot. So that is the exceptional progression quality, right? So it goes from poor to worse. That's how the arrival types are defined. So you have to match it in the right order. Okay. So that particular order is given in option B. Okay, question 9 is when demand exceeds the capacity for a significant period at an approach of a signalized intersection, so you have to choose which statements are correct here. Okay. So option A is every green interval will fail. Option B is the residual queue of vehicles dissipates at the end of the analysis period. Option C, at the end of the analysis period, the departure function catches up with the arrival function. Option D is the overflow delay component grows over time and dwarfs the uniform delay component. So again, more than one may be correct. Okay, option A. Okay, 2 votes for option A and 1 for option D. Any other options that may be correct? Okay, so A, D. Alright, so the right answer is both options A and option D. Okay, so here we are looking at oversaturated condition, right? So demand is exceeding capacity, so B is more than C, right? So demand has exceeded the capacity, and this is there for a significant period of the time. Okay, right? So for a large time, so this is the condition that is happening. So we know that when demand is higher than the capacity, this will lead to overflow delay, right? So what happens in this case? So your demand is there, your capacity is lower, which means that your departure curve will not go back to your arrival curve, right? So because of the lower capacity, so which means there will be spillbacks, right? So on every cycle, so the departure curve will keep on getting diverging from your arrival curve, right? So as we saw, there will be a constant uniform delay component, and then there will also be an overflow delay component, and this overflow delay will keep on growing, right? So as long as this condition exists, so this overflow delay will keep on growing. So therefore, so every green interval will fail, right? So we are looking at it successive intervals. So failure means what? The queue is not fully dissipated, right? So that's what we call as the failure. The departure curve is not going back and touching the arrival curve, right? So that's what we mean by failure. So that happens in all the cycles, right? So in every cycle, we see that this pattern is repeating. So A is correct. B says the residual queue of vehicles dissipates at the end of the analysis period. No, because in our analysis period, V is always greater than C. So residual queue dissipating means the departure curve going back and touching the arrival curve. Why? Because the vertical distance, as I said, is the queue length, right? So if queue length is equal to 0 means the arrival curve is equal to the departure curve, right? So that's when the vertical difference is 0, right? So but that is not happening in our case, which means that there will be some residual queue at the end of our analysis period. So C is at the end of the analysis period, departure function catches up. So again, as we saw, this doesn't happen. And the overflow component grows over time and dwarfs the uniform delay component. True, because the uniform delay part is constant. Okay, so this, if there are n cycles where this is happening, so this is n into uniform delay. But the overflow delay for the first cycle is some small value. Second cycle it is a larger value, and third cycle is an even larger value and keeps on growing, right? So it is not n into OD. So OD is it keeps on growing larger and larger and larger, right? So if we sum up all this, at some point this will be much larger than what is your uniform delay, right? So overflow delay will be much higher. So therefore D is correct. So of the four, only A and D are the correct statements. So the right answer is A and D. Okay, question 10 is which of the following statements are correct with respect to random and the overflow delay models? So option A is simple overflow delay model is a reasonable predictor when the V by C ratio is less than 1.15. B is as the overflow delay model when the V by C ratio is equal to 1, the overflow delay is 0. C is uniform delay is a sufficient predictive tool for delay estimation when V by C ratio is less than or equal to 0.5. And D is as per random delay model when V by C ratio is 1, the random delay is 0. Okay. Option C. Again, there could be multiple options which can be correct. Okay, B and C. Any other answers? Okay, so the right answer are both options A, B, and C. Okay, so first option is simple overflow delay model is a reasonable predictor when the V by C ratio is less than 1.15. Okay, so when V by C ratio is more than 1, so it is an oversaturated condition, right? So here we have uniform delay plus overflow delay as well, right? So in oversaturated condition. So if you are using the simple overflow delay model, so then this part is not accounted for, right? So which means that it won't be a good prediction of the delay, right? So because we are covering the conditions less than 1, but also we are covering the condition between 1 and 1.15, right? So in that region 1 to 1.15, so this model will not perform good. Okay, so therefore A is not good when V by C ratio is more than 1. So that is covered here. So therefore A is not correct. So B is as per the overflow delay model. When V by C ratio is 1, overflow delay is 0. So this is correct, right? So as we saw, when in the inconsistency of V by C equal to 1, so the overflow delay model will be like this, right? So at V by C equal to 1, overflow delay is 0 as per the model, right? So therefore that is correct. So C, uniform delay is a sufficient predictive tool for delay estimation when the V by C ratio is less than or equal to 0.85. This is correct, right? So here we have undersaturated condition, right? And it's sufficiently lower than the capacity. Demand is sufficiently lower. So we cannot expect the random failures also that much, okay? So therefore, uniform delay is more or less sufficient. And D is as per the random delay model, when the V by C is equal to 1, the random delay is 0. So this is incorrect because the random delay is for when V by C is less than 1, right? So here, so it will go like this, right? So at equal to 1, so the random delay, asymptotically increases and goes towards infinity, right? So it's not 0, it tends towards infinity. So therefore, option D is incorrect. So only option B and C are the right answers. Okay, question 11 is the total critical lane volume in vehicles per hour based on the given figure given below is dash. Okay, so we have three different phases. Okay, and different lane group volumes are given. We have to find the critical lane volume for the total cycle. So four options are there: 14, 1140, 1270, 1240, and 1220. Okay, so we have one answer for option B, one for option C. Right, right answer is option C. It is 1240 vehicles per hour. Okay, so how do we do this? So, so the critical lane volume we will do for each phase, right? As I said, for each phase we have one critical lane group, that is nothing but the maximum, the lane group which has the maximum traffic. So here, so we have three actually phases A, B, and C. Okay, so we have to find three different volumes and then sum them. Okay, so for A, so we have for two rings in the controller, ring 1 and ring 2. So again, for each ring we have to see separately. So for ring 1, so we have 140 plus 450, okay, which is 590, right? So for ring 2, we have 250 plus 420, right? So this is 670, okay. So 670 is greater than 590, right? So which means this is your critical group. Okay, so that is for phase A. This we have to repeat for the other two phases as well. So in other two, they are simple phases. Okay, so phase B we have 200 and 220, right? So 220 is greater. So this is the critical group. And for phase C, we have 350 versus 280, right? So 350 is the largest of the two. So now we have to find it for the total thing. So total cycle, the critical volume is nothing but the sum of the individual ones. So we have 670 from phase A, 220 from phase B, and then 350 from phase C. So sum them up, you will get 1240. Okay, so that's how we find the critical lane volume for the whole cycle. Okay, question number 12 is consider an eastbound approach at a signalized intersection with the following known characteristics. Okay, so the 85th percentile approach speed is 60 kilometers per hour. There is an upgrade of plus 3%. There's a width of intersection, which is the distance from the stop line to the far side no conflict point, that is 30 meters. The average length of the vehicles is 5 meters. The deceleration rate can be taken as 2.5 meter per second square. The PRT time, perception reaction time, is 1 second. Entry delay is 1 second. Cycle length is 60 seconds. Green time is 25 seconds. Saturation headway is 2 seconds per vehicle. The startup loss time is 2 seconds and the clearance loss time is 1 second. Okay, so these are the signal configuration that we have. Okay, different parameter values. So what we want to find first is the LO change interval in seconds for this eastbound approach. Okay, maybe two minutes. You have to find the LO change interval, which is small y, right? Small yi. So I is the eastbound approach. Any answers? Shall we look at the answer? Okay. So let's look at the solution. Okay. So here we are asked to calculate the yellow change interval. Okay. So how do we calculate yellow change interval? So yellow interval is nothing but TR plus 0.28 V85 divided by 2A plus 19.6 G. Okay. This is the formula, right? So what is the different components in this? So TR is nothing but here perception reaction time. Okay, so PRT, right? The reaction time, and then V85 is your 85th percentile of the approach speed, and A is your deceleration rate, and G is the the gradient, right? So in percentage. So reaction time is given as 1 second. Okay, so it is 1 plus 0.28 into what is V85? It is 60 kmph, and in the formula we use the V in kmph, and 2A, A is 2.5 meter per second square deceleration rate, so 2 into 2.5 plus 19.6 into gradient is 3%, but we have to use in decimal format, so it's 0.03. Okay, you substitute that, this will come out to be approximately 4 seconds, right? So the right answer is 4 seconds for the yellow change interval. Okay, so next question is, what is the value of the red clearance interval or the all red interval AR in seconds for this approach? Okay, so we have one answer as 1.09. Any other answers? Okay, 1.1. All right. So 1.1 is correct, right? So how do we find the all red interval? So all red interval is equal to the width of the intersection plus the average length of the vehicle divided by 0.28 into V85, minus the startup, the startup delay TS. Okay, so here in the problem, W is given as 30 meters, and the vehicle length, average vehicle length is 5 meters, right? So 30 plus 5 divided by 0.28 into V85 is 60. Okay, minus startup delay, the entry delay is 1 second, right? So therefore, this comes out to be approximately 1.1, right? So 1.09. So if you round it up to one decimal, it will be uh, 1.1. Okay, so all red. So there is no hard range. So it is based on these different factors, right? So depending on your WL, V85, and TS, so it's going to vary, right? So you cannot have a single value or range. So it depends on how these your intersection configuration is, depending on your geometry as well as your vehicle characteristics. So this will vary. Okay, so there is no single range that you can tell, but typically it will be in this 1 second, 1 to 2 second range. It won't vary beyond this, but it can be possible if your design speeds are different. So it all depends on that, but typical range you can say is 1 to 2 seconds. And then question number C is the effective green time for this approach is dash. Third question is effective green time. 13 vehicles per second. No, green time is not measured per vehicle. Green time is the time that is available for all the vehicles, right? So it's irrespective of how many vehicles are going to use, the effective green time is not going to be 13 vehicles per second is not right. Do you need more time or shall we go with the solution? Yeah, 27 is correct. Okay, so let's look at how to calculate the effective green. So the relationship between effective green and the green is like this. So the effective green is equal to the green time plus your change interval time plus the all red time minus the total loss time. Okay. So basically, what is the total amount of time that is available for you to move minus what is the total amount of time that is not utilized to move, okay, out of that period. So your green time you can use the change interval and the all red interval. In all these three, intervals, the vehicle movement can happen, but the total loss time is where the vehicle movement does not happen, even though it could have happened. Okay. So here the total loss time also can be split up. So as the startup loss time and the clearance loss time L1 and L2. Okay. So here in this problem we have green time as 30 seconds. Change interval is we calculated it as 4 seconds. All red also we calculated 1.1 minus the startup last time is 2 seconds, clearance last time is 1 second, right? So minus 2 minus 1. So this will be 27.1 seconds. Okay, so that is your effective green time. Okay, next we have D. What is the capacity in vehicles per hour per lane for the eastbound approach? Okay, S is 1800. Okay, but S is saturation flow rate, right? Saturation flow rate is not the same as capacity. Okay, saturation flow rate happens in ideal condition, right? So when you have 1 hour of green available, right? So the vehicles are continuously moving. So that's when you have your saturation flow rate. Yeah. So CA is 1800 into 27.1 by 60. Yes, that is correct. 813, right? So the relationship is your saturation so capacity is equal to the saturation flow rate for that phase divide into the effective green ratio, okay, which is GI by C. Okay, so we have to calculate the saturation flow rate. So saturation flow rate is 3600 by the saturation headway, which is given as 2 seconds per vehicle, right? So that is 3600 by 2, which will be 1800 vehicles per hour. So your capacity will be saturation flow rate into effective green ratio. So effective green we calculated as 27.1 divided by cycle length is given as 60 seconds, right? that is by 60. And this will be 813 vehicles per hour. Okay, so that is your capacity. Okay, the final question is, if the eastbound approach has an approach flow rate of 600 vehicles per hour, what is the uniform delay per vehicle in seconds per hour expected under these conditions? Okay, so now we are given with the inflow. So we have to calculate the uniform delay. Yeah, value of x is near 0.7, that is correct. So what is the uniform delay? Yeah, 13.49, correct. Yeah, that is the uniform delay. So how do we get this? So as he did first, so first we have to confirm whether the uniform delay model is applicable or not, right? For the given condition, right? As we saw, uniform delay model is not applicable everywhere, right? So as we saw, it is when the v by c is less than or equal to 0.85. That's when the uniform delay model is good enough, right? So first we have to confirm that. So we calculate the v by c. So what is v by c in our case? So V is the volume that is incoming. Okay, that is given as 600 vehicles per hour. And what is the capacity that we just calculated? It was 813. Okay, so this comes out to be 0.738. Okay, yeah, this is also denoted using x, right? So in the UD model we call it as x. So the V by C ratio, which is 0.78. So this is less than 0.85. So therefore uniform delay model is good enough for this condition. So we can go ahead with calculating the UD using this model. So the uniform delay model, according to it, it is 0.5 into the cycle length multiplied by 1 minus the effective green ratio. Okay, so this whole square divided by 1 by 1 minus here g by c multiplied with x, right? So this x is the v by c ratio as we saw. So this we have all the terms that we need. So 0.5 into cycle length is 60 into 1 minus what is g by c, 27.1 by 60. So this term should be squared, and the denominator we have 1 minus g by c 27.1 by 60 multiplied with x. Again x is b by c, which is 0.738. So this will come out to be approximately 13.5 seconds. Okay, so that is here uniform delay. Again, this is 13.5 seconds per vehicle, right? So every vehicle experiences 13.5 seconds. Okay, so that is the uniform delay. Okay, respect to change difference between yellow and red towel. So I don't understand. Can you elaborate more? So see your yellow interval. So it can have this change yellow change interval small y and all red. Okay. So this all red interval, you don't confuse it with, the red interval. Okay. So this all red interval is given to, for clearing the vehicles that have already entered the intersection. Okay. So you'll have your red, then you'll have your green, followed by your yellow and your all red. So this all red will be part of, your red interval as well for the other approaches. But for the approach which had green, so this will be part of your change interval, right? So y plus AR. So that's why when we calculated here, we added the all red also together with the change interval when we calculated effective green. Okay, Platon ratio. What about Platon ratio? So Platon ratio, as I said, okay, let's go to the next page. So Platon ratio will be the proportion of the vehicles. The ratio would be the proportion of vehicles that are arriving in a particular phase divided by the effective green ratio. Okay, so this is your Platon ratio. Yeah, and based on this, you have the different types of arrival. Yes. So, so what does this mean? So here, let's look at qualitatively how this one will vary. Okay. So when PI is large, so what does this mean? So when PI is large, which means that most vehicles are coming in, arriving during the green phase. Okay, during green interval, which means you'll have dense movement of vehicles, right? So platoon is basically this group of vehicles, right, in your stream. So you have large platoons that are able to pass through your your signal, right? So your intersection. So on the contrary, if you have PA is small, which means most vehicles are coming during the red phase, right? So which means during the green interval, small platoon sizes will go out. So if you look at the discharging queue, because during the green only small number of vehicles are present, so they are discharging at small. So the platoon sizes are smaller. So this is not ideal. So we want more vehicles to be transferred. So relatively, right? So depending on the input volume only. But if you look at red versus green, during the green if you have more vehicles, so that is more ideal, right? So that's what the platoon ratio is trying to quantify. So how much vehicles are coming during the green phase and divided by how much green ratio that you have, right? So for larger green ratios, you need larger platoon sizes, larger proportions that should be arriving in that time, right? So that's how we are getting this. So if this value is overall smaller, which means that your platoon progression is poor, right? So that's what your type 1 arrival is. If this is higher, so you have the best progression, so that is 6. So in between we have different ranges. So we cut, so this we cut this platoon ratios by different levels, and then for each category we say that it is of a particular type. Okay. Any other questions? Yeah, so that is what I have written here. Right? So this is the formula. Pi divided by Ga by C. So Pi is the proportion of vehicles arriving during the green interval. Right? So GA by C is your effective green ratio. Okay. So which means like say if 100 vehicles are arriving uh, in a cycle, right? So out of this, 60 are coming during the green and 40 are coming during the red. So then PA is 60 by 100. Yeah, so what you have written is correct. PR is PI by GA by C. Correct. Okay. So anything else? So this was the last question we had for this week. So if you have any further doubts, you can ask. Otherwise, we can conclude today's session. Any other questions? Okay, what problem? The one that we discussed now. What is the question? Are you talking about this one, the one that we just did? Okay, determine the change interval. Yeah, first part, right? Yellow change. So that is here. So it is calculated as TR plus 0.28 B85 by 2A plus 19.6 G, right? So we consider the reaction time, okay, TR. We can take into account the design speed, the deceleration rate, and also the gradient. So what's your doubt exactly here? Okay, anything else? Yeah, so EB just stands for eastbound. Eastbound means the traffic which is going towards east. Okay, so take a four-leg intersection. So we have traffic going towards the north is called northbound. Okay, going towards the south is called southbound. Towards the eastbound, and towards the west is called westbound. Okay, just to indicate the direction of movement. Okay, so to which direction it is moving towards. Okay, so green effective time. So as I said, so we have the green interval. This is followed by a change interval and the all red interval, right? So the vehicle can legally cross through the intersection in all these three, right? So what is the out of this G plus Y plus AR that is available for you? So what is, what, what portion of this is used, right? So that is what we call as the effective green, okay? So effective green, so ideally, what we want it to be equal to this. Okay. So you want the vehicles to utilize all this and then go. But this physically this is not possible, right? So vehicles cannot exactly stop moving at the end of the all red, right? So they will stop before, right? And similarly, the vehicles cannot exactly start moving at the actual speed just at the start of the green, right? So because they need time to accelerate, get ready. So therefore, there will be some portion of this G plus Y plus AR portion that will be lost, right? So that is unutilized. So that portion has to be reduced. So that's where we subtract the startup loss, which is at the end, which is at the start of the green, and the clearance loss time, which happens towards the end of the this portion, this period. So that if you take the difference between this available portion and the lost portion, you get the effective green. Okay. Alright, so there are no further questions. I think we can wrap up the session for today. Right. So thank you for attending. We'll continue our sessions, from next week. Okay, same time. Okay, thank you.